Assalamu alaikum. We know electric power is generated at the power stations, which are located far away from the city or town. In order to transmit the power generated in the power station, transmission lines are used. This process of transmission of electric power from the power station to the consumer is referred as power transmission. In this video, we'll discuss the advantages of AC in long distance power transmission. Now, before going ahead, let me tell you what is AC. We know electric current is broadly classified into AC and DC. Here AC stands for alternating current and DC stands for direct current. What is this alternating current? It is nothing but the electric current in which the polarity, that is the plus or minus sign, varies continuously with time. So it is usually represented by a sinusoidal wave of this kind. This is the positive portion of this wave. This is the negative portion of this wave. Now, as you can see, it varies continuously with the time. Whereas in case of direct current, the polarity is fixed. Okay? And direct current have zero frequency, whereas alternating current provides some frequency. It may be 50 or 60. This is all about the alternating current and direct current. Now, what are the advantages of alternating current in a long distance power transmission? Let's discuss that here. Now, before going ahead, let me tell you one thing about the alternating current. When I talk about alternating current, it is very easy to produce it. And the second, the voltage of alternating current can be increased or reduced easily with the help of transformers. Well, you know very well, when electric current is passed through a conductor, two kind of effects takes place. One is the heating effect, second one is the magnetic effect of electric current. But here, when we are trying to transmit electric power from the power station to the consumer with the help of transmission lines. Now, many times I have used the term transmission line. What does this transmission line represent? Here, transmission line is nothing but the wire or cable used to carry electric power from the power station to the consumer. Okay, when you pass electric current through a wire, certain amount of electrical energy gets converted into heat energy due to Joule's heating effect. Okay, this Joule's heating effect results in the power loss. So, the power loss due to Joule's heating effect is represented as I square R. How do we get this? We know the expression for power. Electric power is the product of voltage and current. And we know Ohm's law. What is Ohm's law? Ohm's law. Ohm's law says that V equals to IR. If we substitute this in the place of V, what do we get? We get this. V becomes equal to, in place of V, I write IR. Now it's multiplied with I. So P becomes equal to I square R. This is how we obtain this expression, which represents power loss in transmission lines due to Joule's heating effect. Okay. Now, if the current passing through a transmission line is nothing but alternating current, then the power loss can be minimized by increasing the voltage. And before that, let me tell you how one can reduce the power loss. From this expression, it is clear that the value of P, that is the power loss, can be reduced if we decrease any one of these parameters. So, if I reduce I value, then this will result in the reduction of P value. In a similar way, if I reduce R value, then also P value can be reduced. What has to be done to reduce the value of R? So I told you we pass the electric current through a wire. Now, the wire is a kind of a conductor. We have studied long ago that R, the resistance offered to the flow of current by a conductor, is found to be directly proportional to length of the conductor, and it is also found to be inversely proportional to the area of cross section of the conductor. Here, cross section area represents the thickness of the conductor or thickness of the wire through which we pass the electric current. So, according to this relation, if we increase L value, R value will increase. So, as the distance between the power station and the point, the destination, where do you want to transmit the power, increases, we need to increase the length of the transmission line. By doing so, definitely the value of R is going to increase with increasing L value. Okay. So to reduce this, we need to increase the thickness of the wire or cable used in the transmission. So if we reduce this, R value will reduce. But if you want to reduce the thickness of the wire used, then the cost will increase. As we increase the thickness, its weight will increase accordingly. The mass of the wire will increase. So to hold such heavy electric cables, we need to install heavy towers. So it adds on to the cost. So this method is not economical. The second method, if we reduce the current, the power loss can be minimized. We know electric power. Well, here I have explained you. Electric power is the product of voltage and current. Now suppose I plan to reduce the power loss by reducing the current. If I do so, you see, according to this relation, when I reduce current, then I have to increase the voltage to keep the value of P constant. Clear? No? So, when we use alternating current, the voltage can be varied very easily with the help of transformer. There we do the reverse thing. Instead of changing the current, or to change the current, we vary the value of V. Now, by increasing the voltage, the current value can be reduced to minimize the power loss. So, AC current plays a very important role in the power transmission at low power loss, okay, with a less power loss. Now, let's explain this to you with the help of a simple diagram. Now, consider this one as a power station. Power station where electric power is generated. This power station is located far away from the city or a town. Here, what is done? The electric power which is generated is made to transmit with higher voltage. So I use a step transformer is used here to increase the voltage. In case of a step transformer, the number of turns in the secondary coil is more than the number of turns in the primary coil. This is primary coil, this is secondary coil. As you increase the number of turns, the voltage will also increase. Okay. Then here voltage is low. Here the voltage has increased with the help of this step up transformer. Right here. Step up transformer. Then the step up transformer is compared to transmission line. Transmission line is nothing but cable or wire through which will pass electric current. Okay. Then on the other end, the voltage is reduced based on the usage. Based on the requirement, we reduce the voltage. For that, we use transformer again. Now this time the transformer used by us is nothing but step down transformer. Now here, in case of step down transformer, the number of turns in the primary coil is more than the number of turns in the secondary coil. See, number of turns in the secondary coil is less compared to the number of turns in primary coil. So we call this kind of a transformer as step down transformer. Step down transformer. Here, transformer can be used to reduce or increase the voltage of alternating current. Whereas when we talk about DC, we cannot use a transformer to reduce the voltage of direct current. You remember that. Then next step is given to the substation. Okay, located at a city or a town. City substation. Substation. Right. This is how power is transmitted from the power station to the substation via transmission. Here dotted lines represent transmission lines. Transmission lines. Okay. Now from this you might have understood the power loss in the power transmission can be minimized if we transmit the power at a high voltage. Okay. Now this I will explain with the help of a simple example. Let's say from a power station, an electric power of 2 megawatt is transmitted via a transmission line which provides a resistance equal to 40 ohm at two different voltages. First, I take the voltage to be equal to 10 kilovolt. Then in the second case, I will take the voltage to be equal to 100 kilovolt. Now, let's see what will be the percentage of power loss in these two cases. Now, I will calculate this one by one. First, I take case 1, which the power is a 2 megawatt, R value is 40 ohm, and voltage is kept equal to 10 kilovolt. Here, K stands for kilo, and it is nothing but 1000. So 10,000 volt. Then V equals to 10 into 10 power 3 volt. Okay, this is what it means. Now, before going ahead, I am going to find out the value of I. Well, we know electric power. Letter P is the product of voltage and current. Now, from this, I equals to P upon V. And what is P here? 2 megawatt. Mega means 10 power 6. So 2 into 10 power 6 watt divided by voltage. Voltage is a 10 into 10 power 3. Now from here. Now let's simplify this. When I multiply 10 with the 10 power 3, it becomes 10 power 4. So 10 power 3, this is the correct answer. Now what do I get is 10 power 2 now. Okay. So the value obtained is equal to the I value is nothing but 2 into 10 power 2 measured in ampere. Okay. The 10 power 2 means we multiply 10 twice. 10 into 10 is 10 power 2. So when 10 is multiplied twice, we get 100. 100 multiplied 2 is 200. 200 ampere. This is the value of I for the first case. Now I will calculate the power loss. So, power loss. Power loss in the form of heat energy. Is known as I square R. So this I obtained from here. Okay. Now I'll substitute the value of I and R here. What is the value of I? Is 200 multiplied twice because we have I square. So 200 multiplied with 200. Then the value of R is about 40. So what I get? The 2 multiplied 2 is 4. 4 multiplied 4 is 16. Now how many zeros we have? 1, 2, 3, 4, 5. 5 zeros. So I write it like this. 10 power 5. So this is the power loss. 16 into 10 power 5 watt. Or 1.6 megawatt. This can be written as 1.6 10 power 6 watt or 1.6 megawatt in simple word. Okay, this much of power gets dissipated in the power transmission when the power is transmitted at a lower voltage. Okay, now I'll calculate the percentage of power loss. To calculate the percentage of power loss, I take this term, power loss, 6 into power 6. Then I divide by the total power transmitted is 2 megawatt. That's 2 into 10 power 6 watt. Then the whole term is multiplied with 100 to get the value in percentage. You see what I get now? This and this get cancelled. This get cancelled and I get 0.8 here. 0.8 multiplied with 100. 0.8 multiplied with 100 is equal to 80. So 80% power goes waste. When we transmit 2 megawatt power generated in power station at a 10 kilovolt. Okay, now I will calculate the power loss, percentage of power loss if we transmit the electric power to high voltage. Case 2. Case 2. Case 2, power remains equal to 2 megawatt. R is 40 ohm. But the value of V. What's the value of V? Value of V is taken as 100 kilovolt. Right? Now first I will calculate the value of I. from this expression. I equals to P upon V. This we have obtained from here. I equals to P upon V. Now I substitute the value of P. 2 into 10 power 6 watt divided by voltage. Voltage is 100 kilo. Kilo means 10 power 3000. So I simplify this. What do I get if I do so? There 10 power 3 multiplied 100 is 10 power 5. So I get 10 here. So the value of it is equal to 2 into 10. That is the 20 ampere. The current value is 20 ampere here. This one to be equal to 20 ampere. Now the power loss is obtained using this power loss. I square R. This is the value of I and R here. 20 multiplied by 20. The value of R is, what is that? It's 40. So what do you obtain here on multiplication? 2 into 2, 4, 4 into 4, 16. How many zeros do we have? We have 3 zeros. 2, 3. This is the power loss. This is the 100 watt. Clear? Then percentage of power loss. Percentage of power loss can be obtained if we divide this 16,000 divided by total powers transmitted is 2 mega. 2 into 10 power 6 multiplied with 100. Now, here 16,000 calculated as 16 into 10 power 3 divided by 2 into 10 power 6 multiplied with 100. Okay, now see, I simplify this. First, 10 power 3 is this one. When 10 power 3 multiplied with 100, we get 10 power 5. When we cancel this 2, we get a 10 here in the denominator. Then next, when these 2 are divided, we get 8 here. So the next step, the value obtained is equal to 8, and here the denominator we have 10. So 8 divided by 10 is 0.8. 0.8. Okay, 0.8%. Earlier we obtained the value to be equal to 80%. Now it has reduced to 0.8%. This clearly shows that if we transmit electric power at high voltage, then the power loss can be minimized. So this is what we understand from this topic. For the power transmission, if we increase the voltage, then the power loss can be minimized. And the variation of voltage becomes easy in case of alternating current, whereas in case of direct current, it's a difficult task. I hope the video is useful. If you have any kind of doubt related to the topic, can you put a question in the comment section. Thanks for watching.